So in the last class we saw the frequency domain representation of discrete time signals and systems, where we studied the concept of eigenvalues and eigenfunction in the sense that we have y of n is equal to e to the power j omega e to the power j omega n. So this we have denoted as the eigenvalue and this is the eigenfunction. Okay, so today we will see some of the properties of this function by seeing the discrete time Fourier transforms. So given the discrete time, let's say Fourier transform, we can represent many sequences by the Fourier integral x of n as 1 over 2 pi from minus pi to pi j omega n d omega. Okay, so given any this function x of e to the power j omega, many of the sequences can be represented by this, where we have seen in the last class also that x of e to the power j omega is basically the summation over k minus infinity to infinity of x of k e to the power minus j omega k. Okay, so this possibly you have come across for the very first time in your signal systems class, where we call this the Fourier transform of the sequence x of k, and this is the inverse Fourier transform. Okay, and the overall we call them the Fourier representation. For the sequence. Okay, now an important question arises here. Does this Fourier representation exist for all types of signals, or let's reformulate it in the sense that we want to determine the class of signals that can be represented by this inverse Fourier transform, basically by this thing. Okay, so as we have been discussing in the last couple of classes, that for this, since this include there is an integral of x of e to the power j omega to represent any sequence in this form, we want this x of j to answer this question. We want that x of e to the power j omega should be integrable, right? If this term is integrable, then we can see that what all classes of sequences or signals can be represented. So basically we are interested in the, and we saw and we know that x of e to the power j omega is represented by this summation of sequence. So we want the convergence of this infinite sum for k from minus infinity to infinity, right? So let's see. So what do we want? That x of e to the power j omega should be bounded, meaning to say the absolute value of this function should be less than infinity for all values of omega, right? Now we know from the above, from the Fourier transform, that x of e to the power j omega is basically the summation over k or n xk, let's write it n to be consistent, x of n e to the power minus j omega n, this one, right? And we know that this absolute value is less than or equal to their individual absolute values inside the summation, that should be less than or equal to summation over n mod of x of n and mod of e to the power minus j omega n, and we know that this is equal to 1. Okay, so what do we want, or what it gives? mod of x, okay, should be, and if we want that this condition to be satisfied, we want that this should be less than infinity. Okay? So it says that the summation of that sequence should be a finite number, and this is nothing but the sufficient condition. Okay, we will come on to this aspect a bit later, but there are two important points to note here, that if you have the sequence x of n and this sequence is absolutely summable, which says this condition, that if the sequence xn is absolutely summable, then the transform x of e to the power j omega exists. Okay, you can also say in terms of the finite energy, that if x of n is of finite energy, then its transform x of e to the power j omega exists. Right? From our earlier discussions also, we briefly discussed about the FIR systems, or the finite length sequences. So any finite length sequence is absolutely summable. So for that also the Fourier transformation representation exists. Okay. Now coming on to this aspect of this sufficient condition. This sufficient condition says that if this condition is satisfied, then you can have the Fourier transform representation. But since it's only a sufficient condition, there might exist other signals also for which the Fourier transform still exists. Right? For example, we can see some basic types of signals which we have been discussing earlier. Let's say x of n is equal to 1 for all values of n. We know that this signal is neither absolutely summable nor having a finite energy or square summable. But still, we know, or we had seen earlier, that the Fourier transform of this sequence is given by this. So it is only the previous condition what we have computed, determined, was only the sufficient condition. But we can see how now. Okay, because now we are interested in that what all other signals or the sequences can have a Fourier transform representation. Right? So here first of all we will consider the general case where, let's say, we have x of e to the power j omega is given by r is equal to minus infinity to infinity 2 pi del omega minus omega naught plus 2 pi r. So we have included this term omega naught. Right? So now substituting this in the inverse Fourier transform expression we had seen, in this one. So we will substitute this x of e to the power j omega there, and we get x of n as 1 upon 2 pi from integral from minus pi to pi summation of minus infinity to infinity 2 pi del omega minus omega naught plus 2 pi r times e to the power j omega n d omega. Right? So since we have this integral for all omegas ranging between minus pi to pi, we only require to analyze this integral for r is equal to 0, because this part will also repeat itself. So substituting this r is equal to 0 in the above expression, we get 1 upon 2 pi. D omega. Okay, so this is your x of n. Now using one of the properties of the impulse function, which we also call the generalized function, that if I take the integral from minus infinity to infinity of del of x multiplied by f of x dx, then it is equal to f of 0. This is the property of the impulse function. Now if we, let's say, if we are given x of n as e to the power j omega naught n for any n, then you can quickly see that if I put omega naught is equal to 0, you will get xn is equal to 1 in the above expression, right? So for all such signals, because here we have also considered the x of n, where we have the omega naught because it is already generalized. Now for such kind of sequence, which is e to the power j omega naught n, we know we can compute its Fourier transform as n minus infinity to infinity j omega naught n xn e to the power minus j omega n. Yeah, and this is equal to what we had above, this expression. For r is equal to minus infinity to infinity 2 pi del omega minus omega naught plus 2 pi r. This is also a generalized function. Right? So this aspect shows that the concept of Fourier transform representation can be extended to the class of sequence that can be expressed as your x of n for summation over k ak e to the power j omega k, where you have n ranging between minus infinity to infinity. So if you can represent your sequence in this form, then for those sequences, because still some for some of the represent, or for some sequences might not be absolutely summable, which you can put into this form, like you have the unit step sequence. So for all those sequences, you can compute or you can have the Fourier transform representation as r minus infinity to infinity summation over k ak 2 pi del omega minus omega naught plus 2 pi r. So this would be your x of e to the power j omega. Right. So first we saw what is the sufficient condition for any sequence to have a Fourier transform representation. We saw that it should be absolutely summable, or it should have a finite energy. But we notice that this is only a sufficient, meaning to say there might exist some other types of signals also, for which you can still have the Fourier transform representation, which are not absolutely summable, or they have the finite energy. So one of the case we saw where you have x of n as the unit step sequence, and then we come to the conclusion that if you can represent your sequence by this representation, then for all those sequences you can have the Fourier transform representation. Of course, the another type of sequences, you have x of n is equal to unit step sequence un, where e to the power j omega is given by 1 minus e to the power minus j omega plus summation r minus infinity to infinity pi del omega plus 2 pi r. Right? So you can try to compute this Fourier transform for this unit step sequence. The above one is having the value of 1 for all values of n. So it was not exactly the unit step sequence, because unit step sequence take the value of 1 for n greater than or equal to 0. But the sequence we saw in the earlier example was taking value 1 for all values of n. Okay. So again, you can try to represent this one into this form, and finally to have this representation. Okay. Next, we see the Fourier transform, some properties of the Fourier transforms, or you can call them the basic theorems, which would be useful in a later discussion. Okay, so we most of the time we will use this denotation that x of n. If we take the Fourier transform of this sequence x of n, we get x e to the power j omega, and in on taking the inverse Fourier transform of this x of e to the power j omega, we get x of n, right? So we see most of the time we represent like this in a single notation. Okay. So for all this theorem or the properties, we shall not discuss the proofs in details. We will see the significance of those properties, because most of the properties you can derive by yourselves by doing some simple manipulations of variables, of summations or integrations. Okay. So the first property is the linearity, which says that if for given x of n, x1 of n, if you compute the Fourier transform and you get x1 e to the power j omega, and for another sequence x2 of n, you get x2 e to the power j omega. Now if you form another sequence by multiplying the sequence 1 by scalar a and the sequence 2 x2 of n by some scalar b, then the Fourier transform would be this one. Okay, which is basically comes from the principle of superposition, where in this both the properties homogeneity and additivity are combined. Okay, time shifting and frequency shifting. Again, let's say you have x of n with Fourier transform x of e to the power j omega. If I shift the sequence x by nd number of samples, then on taking the Fourier transform of this sequence, it will give you e to the power minus j omega nd times x of e to the power j omega. Okay. This is the shifting of time. Now we see the shifting of frequency, that is on the right hand side, that if you have a representation, the Fourier transform representation x of e to the power j omega minus omega naught, I have shifted the frequency, then it is of the sequence which is given by x of n times e to the power j omega naught. Okay, so here we have the time shifting, here we have the frequency shifting, and their respective effects on the time domain and the frequency domain. The next property is of the time reversal. That if I reverse the time in the sense that I want to compute the Fourier transform of x minus n, then you would have e to the power minus j omega. So this negative sign will appear. So if you reverse the time, you need to reverse the sign of the frequency on the right hand side. Differentiation in frequency. We can see the differentiation in frequency because x of e to the power j omega is continuous with respect to omega, right? So again, given x of n having a Fourier transform x of e to the power j omega. Now if I multiply the sequence n That is, I want to compute the Fourier transform of nxn, nx of n. Then it is given by j times uh, derivative of this function with respect to omega. Okay. The next property is, or the theorem which is quite important, Parseval's theorem. Which says that if you have x of n again, then if you are interested in computing the energy of this sequence, which is given by, which is the square summation of this sequence, then it is given in terms of the frequency as 1 upon 2 pi, integrating from minus pi to pi omega d squared omega. There, this what you call the energy density spectrum. Okay. The next properties of the convolution. We had seen earlier also, but let's put all the properties at one place so that it is easier for you to recall and go a bit deep into these properties. So for the sequence x of n, if the Fourier transform is x of e to the power j omega, and you have the another function h of n, which we have been using to denote the impulse response. And for this h of n function, let's write the Fourier transform representation as h of e to the power j omega. And if I want to compute the response of the system, which we had seen earlier, by the convolution from k minus infinity to infinity, x of k h n minus k, or x of n convolved with h of n, then in the frequency domain you can compute as the simple multiplication of their transformed counterparts. Meaning to say, for x of n, you have x of e to the power j omega times h of e to the power j omega. Okay. So the convolution in time is merely the multiplication in the frequency domain. Okay. The next property is the modulation or windowing. So if you have x of n having Fourier transform e to the power j omega, and some another function w of n having its Fourier transform representation as w e to the power j omega, and if you want to compute y of n, which is given by the multiplication of x of n and w of n. So here we are seeing the multiplication instead of the convolution. Then y e to the power j omega is the convolution in the frequency domain. So 1 upon 2 pi minus pi to pi x of e to the power j theta times w of e to the power j omega minus theta d theta. Okay, so note that we are taking the theta ranging from minus pi to pi, so it would be a periodic convolution. Okay, now we can see a very quick example for computing the impulse response for a difference equation. Let's say we are given some difference equation y of n minus 1 by 2 y n minus 1 is equal to x of n minus 1 by 4 x n minus 1. So here we will see how we can use the above properties to actually compute the impulse response or the actual response for some input to the system. This is some system defined by this difference equation, and if you are interested in computing the impulse response, which says that x of n, when we apply x of n is delta of n, we want to compute the response, which we denote by h of n. Okay, so let's substitute this in the above equation. We have h of n minus 1 by 2 h of n minus 1 is equal to delta of n minus 1 by 4 of delta n minus 1. Okay, now taking the Fourier transform both sides. So for h of n we have h e to the power j omega minus 1 by 2. So here we have the time shifting, and for time shifting we use the property e to the power minus j omega h e to the power j omega. So the time shifting property was this one. So if I shift the function by n minus nd, then on the right hand side, whatever be the Fourier transform we have for x of n, it is multiplied by e to the power minus j omega times the number of shifted samples. Here we have only 1, so we would have e to the power minus j omega times e to the power j omega is equal to, for delta of n, the Fourier transform is 1, and again we have the shifted, so I can write straightforwardly e to the power minus j omega times 1. Okay, so simplifying this equation, the impulse response in the frequency domain is given by 1 minus 1 by 4 e to the power minus j omega divided by 1 minus 1 by 2 e to the power minus j omega. Okay, now we are interested in computing the impulse response in that time domain. So we have to compute the inverse Fourier transform of this function, and the first step is to do the partial fraction of the right hand side. So you can, the partial fraction for this function is pretty much simple, which is 1 over 1 minus 1 by 2 e to the power minus j omega minus 1 by 4 e to the power minus j omega divided by 1 minus 1 by 2 e to the power minus j omega. Right? So there is some table which you can refer from one of the textbooks we are following in this course. There, in this table, there are some specific inverse Fourier transforms are given for some functions. So when you do the partial fractions, you obtain those functions directly or by simple manipulations. So for this function, which is the first one, 1 minus 1 by 2 minus j omega, you have the inverse Fourier transform as 1 by 2 n u of n, and for the another function minus 1 by 4, which is the second term on the right hand side, 1 minus 1 by 2 to the power minus j omega. The inverse Fourier transform of this is 1 by 4, 1 by 2 n minus 1 u n minus 1. Okay, so since it's linear, it satisfies the linearity property. You have h of n, you can write directly as 1 by 2 n, the first part, u of n minus the second part, 1 by 4 2 n minus 1 u n minus 1. So this would be the impulse response for the given difference equation by using the properties. Okay, so we can stop here, and from the next class we can start with the Z transforms. Okay.